Good afternoon, everyone. Greetings from EJS India. Welcome to the monthly webinar as a part of the series on Design Without Errors. The topic for today's webinar is on best practices in design engineering using SolidWorks. We are happy to have with us Mr. Natarajan, Managing Director of EJS India, to provide his insights on the topic. A postgraduate in mechanical engineering from the University of Toledo, Ohio, USA, Mr. Natarajan R. started his career at Ford Scientific Research and then moved on to Alpha Simultaneous Engineering, a flagship division of Ford Motor Company, a USA working on new vehicle designs and technologies. Having extensive experience in design across various industries, Mr. Natarajan brings deep knowledge in engineering design. He has been actively associated with the Bureau of Indian Standards in various sections relating to engineering drawing and material handling. Well known for his GD&T programs and FVA courses, Mr. Natarajan emphasizes on the design for quality and reliability to the mainstay in engineering design. I invite Mr. Natarajan to deliver today's webinar on best practices in design engineering using SolidWorks.
Thank you. Greetings to all of you. Today's webinar is an interesting topic on best practices in design engineering using SolidWorks. Before we get on to this topic, while many tools and technologies are available today, SolidWorks, which is 30 years old since its first release, has gone through many transformations based on the feedback from the users, the voice of the customer, and it has enhanced itself quite a bit, transforming itself from mechanical engineering tool to a mechatronics tool. The agenda of today's presentation is about a brief about EGS India for those who are new to this webinar series. Then we will emphasize on the design for Q&R, which is quality and reliability process, achieving the same thing step by step, summarize it with the benefits, and then leave the floor for question and answers. This webinar is a part of the Design Without Errors series that we have been conducting since November of last year. Specifically in the area of design, if processes are followed meticulously, the quality and reliability can be assured. Having started our operations in 1993, our vision has been engineering development through effective partnership, trying and achieving the same through the mission statements, imparting leading edge technology, training and development to customers, problem solving and new product development through our engineering services, and providing software solutions and technical support. This we have been doing for the last 3 decades. EGS India was started from our parent organization, EGS Incorporate USA, which was started in 1981. In India, we commenced in 1993 after I returned from the US. In 97, we started our academics trainings division. We started becoming associated with SolidWorks Corporation just after 1999 beginning. And we have been with them on this course for the last this is our 26th year. We commenced our Coimbatore operations just at the beginning of 2007, followed by Trichy operations in 2009. And we became an independent company in 2007. Actually 2003, then ratified in 2007. We shifted to our own headquarters in Chennai in 2011. We have been developing our own softwares and technologies, and we launched the Live PLM, the product lifecycle management. And then subsequently, right now, we are in the process of releasing next month the Live QC tools, which is an indigenous quality software. Our company, we have been in existence for the last 32 years with over 140 people, having offices in Chennai, Coimbatore, and Trichy, with over 2,000 customers, with affiliation to Bureau of Indian Standards, Society of Automotive Engineers India, IMTMA, IPI, Indian Plastics Institute, MMA, National Institute for Quality and Reliability. And mainstay for us is innovation in our processes, in the technologies that we developed for customers, with the main denominators being cost, time, and quality. And this we have empowered our customers, and over a period of time, we have gathered enough knowledge that we have started developing software specific for the industry usage. Our business model is we have three divisions, starting with engineering services, where we do product design and development, whether it is a watch or a machine or an aircraft part or a light combat aircraft equipment or a validation of a gearbox or whatever it is. And design validation is our mainstay, with dimensional management and value engineering being intrinsic in the processes. The process what we are going to enumerate today is what we cover in our engineering services. And we have been associated with Dassault Systems for their Solidworks suite of products and Simulia, and we work with them in implementing the Solidworks PDM across main domains and the 3D Experience PLM platform as well. In addition to that, we have the live PLM, which works on top of the SolidWorks PDM, and we are bringing out the quality control tools next month. The technology training that we offer is well sought after by the industry, specifically in the area of geometric dimensioning and tolerancing and tolerance stacks, failure modes and effects analysis, design for manufacture and assembly, and popular CAD FEA tools. Now, the design for quality and reliability process that we tell our customers to incorporate as a part of their new product development and process-centric activities in design is shown here. You start enumerating the quality and reliability objectives when you start designing a product. These need to be measurable objectives. You classify them into assembly and performance objectives. The assembly and the performance objectives are driven by the design failure modes and effects analysis, which is nothing but a risk management tool that we need to use to look at the severity, occurrence, and detection. The RPN has been dispensed with since 2015. And then it drives the assembly objectives, while it also gets influenced by the performance objectives. On the performance objectives, we look at evaluate the design for performance, design for life, not the factor of safety, because design for life is the mainstay these days. Design for safety, packaging, and transportation. While on the other side, we look at the assembly objectives and look at the design for assembly, with the basis of that forming the datums getting enumerated and the datum reference frame coming into picture, and the part feature tolerances getting enumerated, and using that to perform the tolerance stack-up analysis. And while doing the tolerance optimization for maximizing the tolerance for the least cost, we use the objective function that comes from your tolerance analysis, while the constraints come from the SOD, which is nothing but the severity, occurrence, and detection from the DFMEA, the CPCPK from the manufacturer, design for manufacture, as well as the design for cost objectives being the cost of precision and cost of poor quality being the constraints. Putting them together, we optimize the tolerances and get the key characteristics that need to be put on the drawing, which have a higher SOD denominator, and then releasing the product specification drawing using GD&T. Taking into considerations the design for manufacture, design for cost, design for service, and any other design considerations that may affect the fit, form, and functional requirements. The three pillars in design are specifically fit, form, and functional requirements. While we enumerate all these three things, we look at the voice of the customer, we look at our product definition, and we translate them into measurable specifications on drawings. Between the idea and the end drawing that is being released and the finished product which is being launched in job one, the process that we need to go through is very critical. Remember, every consumer of your engineering drawing is internal as well as external. If the general arrangement drawing has to be blessed by the customer before you sign off, it gets consumed by the customer. Otherwise, the stakeholders inside the organization are the predominant consumers of your drawings. So any mistakes that you do on the drawing, it could be fit related, it could be form related, it could be function related. Finally, it translates into quality issues and reliability issues. So the three pillars of design, while keeping them in the mainstay, we need to focus on the process that we have just enumerated. You look at the SolidWorks interface, you see embedding design knowledge over there in terms of equations, in terms of driving parameters that would drive your design parameters inside your popular CAD tool that you love called SolidWorks. Now, these equations are driven based on knowledge, based on engineering principles, based on many considerations that are coming in. So you can use your equation editor, you can use an external text, you can manage all these things for standardized parts. I hope you are able to see it. And you will be able to embed the knowledge inside the system as a part of your process. This is important. Why is it important? Embedding the design knowledges. If the design carries forward from one person to another, and also to the design reviewer, what knowledge has been considered, what has not been considered, is taken into consideration while approving the designs. The next thing is, you look at the design binder. This is one thing which is not used extensively by the design fraternity. We have to incorporate the processes in design and look at the considerations of the same and document it as a part of the process. So when you put the design process together, which needs to be visible to the stakeholders, and you assign tasks to them and deliverables, these have to find themselves as a part of your design documentation. What best place to put it other than inside SolidWorks itself? Why is this required? Again, knowledge, ensuring that the considerations have taken into consideration the voice of the customer and many things downstream. You can put every one of them inside your design binder. Now, when you're establishing SolidWorks and you're using the design tool, you can put it as a part of your template itself. I have given you a few in this part, but some things will come in assembly. Some things will come in drawings. A lot of different things will come into picture. The ISO 9000 talks about risk management with the emphasis on risk management. How is design addressing that? All these things can be put forth in a visible manner, going through the approvals processes in the organization in a painstaking way. So you're moving away from a person-centric design to a process-centric approach to ensure that all the puzzle elements fall in place for the big picture. And that is quality and reliability. So you can put any different kinds of documents. Here, some documents are shown. The design journal, which comes by default, the design for manufacture and assembly, fault tree analysis, FEA report, FMEA, process capability, quality function deployment. Many things can be put over there. See, for example, you look at the DFMEA, QFD has become a mainstay in addressing those requirements to make sure that what if the failure happens with regard to the voice of the customer not being met. The FMEA needs to address that, right? So the quality function deployment in terms of a centralized QFD house of quality tree that gets put by your marketing and your product definition team can be linked to your product design specifications that are coming in your 3D CAD tool. So every time the document over there changes, it will get updated every time you open the file here. Now, what are all the different things that you have adhered to? You have considered, for example, in this case, customer requirements are noise levels less than 60 dB, heavy duty application, low wear, infrequent oil change, low vibrations. Then at the part level, you translate them into measurable specifications. This is exactly where we look at all these measurable specifications. It could be in terms of the dimensional parameters. It could be in terms of the material procurement or material heat treatment and material institute data that you're taking subsequently down the line to evaluate the material properties are conforming to the requirements or not. All these things you are visibly putting there and saying these are all the parameters that are going to be influencing the voice of the customer requirements. So needless to say, these become the mainstay in the inspection as the outcome from the process when you are looking at the product launch subsequently down the line, either at the quality assurance stage or after the product launch at the quality control stage. So this is a template which sits inside. I'm just giving you an example. If you keep this file inside the PDM environment, then you can take the information directly from there, and every time the version gets updated, you can get the latest version over here. Okay. The next is the design for manufacture and assembly that we talked about in the assembly objectives earlier in the DFQ&R process. Put together the checklist, build upon the checklist based on issues that have come from the manufacturing, from inspection, from your customer, and build this live database in terms of compliance checklist so that adherence to that at the part level, at the assembly level, at the subsystem level, at the system level can be monitored, approved, and released. Now, for example, you look at that checklist thing, which is showing there in the Excel there. Are there standard parts that can be used? Should I create a new gear, or can I use a standard part which is already available? Have I gone through an exhaustive check of already available parts which could be in our inventory or which could be available off the shelf, bought out cheaper as compared to produced in-house? Why is that a requirement? If a standard part is used in an assembly, the reliability goes up many-fold. Why? Because the history of the product is already known. So if we try and use as many checklist items as possible, and if we give due diligence at the design stage, those criteria which could have slipped through the fingers would necessarily get emphasized as a part of the process. So when we put this document inside, these checklists are nothing but things gone wrong and things gone right based on this. So we can put this together as a part of the design binder documents inside and verify the compliance before signing off on the drawing release. Next is, have I considered the fault tree analysis as a part of the risk management? For example, the gear tooth failure. What could be the reason for that? The wear, the pitting failure, the tooth contact wear. So many things are there. Coefficient of friction being one of the lead indicators because of the oil which is sitting inside with the contamination. Contamination coming from where? Right? So a lot of different things come into picture. We do a fault tree analysis. If this is linked to a fault tree analysis already available on the system, then you can come back and say which are all the aspects that you have considered over here, and whether it is many factors coming together or only a few factors coming together. You can put these documents and ensure that people have complied with it. At the part level again, at the assembly level, selection of tolerance, so many different things. For example, if it is tooth wear and if it is pitting failure as a result of knocking because of backlash because of tolerances, you know where the measurable specifications are, right? Next is the failure modes and effects analysis. The design failure mode and effect analysis and process failure mode and effect analysis can be brought inside here itself and linked here, so that the design and the process failure modes can be going to tango. So this is a part of the risk management, right? The failure modes are being prevented and the SODs are being brought in. So you have a lot of different ways. The DFMEA has gone through a huge change these days with the structure diagram, the failure analysis requirements, so on and so forth. All those templates can be put in. The compliance of these templates make sure that our design stays on course. It is not the amount of time that it has taken to design that matters. It is the amount of time that it has taken for the product to be launched that matters. The design time may be a little higher, but the overall development time comes down quite a bit because of all these considerations that have been taken into a fault at the design stage itself. Now, we all know that you can use the Excel tables, you can use the Excel cells, and you can link them to the design parameters inside Solidworks. So if you have a critical to quality dimension, inspection dimension, you can link that to this Excel, which is sitting inside your DFMEA itself, and show it to audit, show it to the people downstream how you have mitigated the failure mode. If the design department is asked to relax the tolerances and you know that the SOD is not in favor of relaxation of tolerance, you have a justification coming in here. So these are the different ways in which this tool enables you to capture the information of the design process, keeping quality and reliability under focus consistently all the time. Next comes the most important thing that typically the manufacturing people and the other people downstream, the planning people, have to look at, which is nothing but the manufacturing process selection. Now, what I'm showing you here is an Excel-based Prima matrix. For manufacture and assembly, Prima matrix is used worldwide. We have just put this together as a spreadsheet-driven decision-making tool inside Excel and embedded it inside the design binder inside Solidworks. So the moment you put this, you can easily go and select the material. Then you can select what is the quantity. Then you can select the manufacturing process according to that and the process type according to that, and go on and on and on and on and on till the final 2 or 3 methods are available. And then you look at, when the design review, you can debate over whether manufacturability has been addressed at the design stage. So when you are doing collaborative engineering and concurrent engineering activities and you are having a design review meeting, these can be deliberated upon and these can be put together. The canvas is provided to you to be as elaborate as possible in incorporating as many processes, as many milestones as possible, as you would be required to protect the quality and reliability. So this is one of them at the part level. Another thing is you can look at the undercut and other things using DFM Express, which is sitting inside SolidWorks. I don't want to debate on that. There are enough videos to go through that. Now the selection of tolerances, you can go through the CP/CPK calculation and you can ask the people to give you the process capability of the machine they are using and put that together on your Excel sheet link it with an external Excel table. So every time the external table gets updated, this will be updated inside the SolidWorks file. So when you open this file, you know exactly what the process capability is. So the lower and the upper specification limit here can be determined directly from design and given to your people over there. So every time it changes over there and you open the file over here, you know exactly where the problems are. And if the customer is coming back, and your customer meaning your manufacturing is coming back and asking you to relax the tolerance, the first thing you can ask is, please give me the process capability. So a lot of things can be brought in and stored in the Excel file. There is another tool called as MIT Calc. And also you have SolidWorks, which is having the TOL analyst. You can use that to also do the tolerance stack-up analysis, to look at and incorporate the process capability to see whether the required process capability is available or whether the tolerances can be achieved or not. The control charts and the histograms can be seen right then and there. You see how powerful you can enable. See, the SolidWorks is a technology enabler so that you can use this information to leverage on the maximum capability that your process or your supplier process can be given, can be used to reduce the overall manufacturing cost and the inspection cost. This is a part of the quality assurance as well as the quality control process upfront at the design stage. Next is when you are doing a design review, you can look at the design, the process, the assembly, and the review can be done meticulously with the concurrent engineering team. I keep getting the chats on the line to maximize the view. That needs to be done on Teams. It is already maximized. The screen maximization. The Excel maximization. That I will provide you the Excel sheets subsequently as a part of the template that you can keep it in your organization. So the design review can be put in and you can have who is, whether it is complete, whether it is open, whether it is not applicable. Everything can be recorded and people can be put in together. Yeah, it is not completely visible because it is a part of the process. So you will be getting the sheets subsequently after this presentation is over, and you can give it to the people who have arranged this. They will be glad to share the same with you. So the design review can be brought in and actionable items can be taken forth. Now the next thing is the design risk assessment. In the design risk assessment, you can look at the past failures. You can document those as a part of the active document. Remember, the design records are active till the components are in service. So these are live documents. You can prioritize them as low, medium, or high, and you can provide the mitigation plan on and on and on at every stage of the way. This is not only for the part level, but also for the assembly level. So when you are looking at the entire picture through the prism of quality and reliability, when you are putting this together, even a graduate engineer trainee who is coming into your organization can go through the process based on these template-driven initiatives to ensure that the de-risking has happened as a result of considerations in design. Now look at this, the fastening process selection in assembly. Again, you can go through the Prima matrix for assembly, and you can look at the fastening techniques. You can look at Poka-Yoke. You can look at the assembly cycle time, because people in assembly want, people in the downline shop floor want the lowest assembly cycle time, right? But then that has to conform to the quality and reliability goals. You change that without looking at the datums, we get into trouble subsequently down the line with more rejections coming in, either at our place or at the customer place. So all these are well documented sitting over here. And you can establish these practices as rule-based either inside Excel or inside SolidWorks. And you can put macros, and you can, what I'm showing you is the tip of the iceberg. Now, the next thing which has become very ubiquitous is the mechatronics design that is getting into the mainstream quite a bit. So the mechanical team and the electrical team or the electronics team have to work hand in hand to ensure that the mechatronics assembly goes through without any risks of failure and meeting the requirements. Herein, you can use the simulation modeling inside the CAD tool. You can use the controlling functions inside your embedded systems. You can go back and forth between the two and do the optimization of parameters with the feedback coming in from the embedded systems. And you can fine tune your mechanical design in terms of choice of motor selection, sensors, the sensitivity of sensors, so many things coming into picture. The speed torque characteristics, so many things coming into response time, so many things there. So how can this be accomplished? There are many ways in which this can be accomplished. Two of them are Rockwell has built tools inside so that you can control it directly from inside the SolidWorks interface itself. From inside Premium, you can use your motion simulation. You can put sensors. You can put your motors over there and then transfer the control over to either the NI, the National Instruments, or the Rockwell Automation, or any one of those drivers. This one in particular is the NI tool, LabVIEW, where you can actuate it from inside the LabVIEW interface, and you can see, go through the motions inside your SolidWorks. Some of our customers are using it. The advantage of this is your response times calculations, your power requirements, your power fluctuations, all those things can be the torque pulsations, the efficiency calculation can be verified at the design stage itself, and it gives you the scope for optimization. For example, you are looking at a special purpose machine, or you are looking at a mechanism design, or you are looking at a VMC or an HMC. You can beautifully do it using LabVIEW with the SolidWorks, and this has been there since 2009 for the last 16 years. So the tool, the SolidWorks, helps you to focus on the system design while keeping the priorities of the part of the assembly intact. This can be done very intrusively, very compulsively inside SolidWorks itself, using these tools and technologies which are available, and then translate it naturally when you are going mainstream with this project with your customer. It is easy. Once you have tested it inside, things gone wrong, gets eliminated, and things gone right, goes up in your list. So the next and the most important thing is the design for cost. 85% of the product cost is determined by design. There are enough documentations to prove this. If we are looking at design upfront, SolidWorks provides you with all the tools for getting to know the design, the cost of the product at design stage itself. And you can do it dynamically by linking to parameters in Excel tables externally and bringing it in. And you can keep churning out these reports from every part, every assembly at the system level, so that you can look at the intrinsic value analysis, value engineering a priori and not posteriori. You don't need to do the value analysis and value engineering after the product has been released, because every tool change is going to cost you money. Might as well do value analysis in the beginning itself, so that fewer value engineering activities are there downstream after the product has been launched. And you give the different cost alternatives to management for them to take a call as to which one to go with, depending on whether the design is a standardized design, it's an evolutionary design, or it's an innovative design, first of its kind in the marketplace, where you can capitalize the market faster. So taking the assessment of the cost contributors coming in and publishing these reports, we know exactly where we need to concentrate on, which costs we need to monitor, tangible and intangible costs, and put them together as a part of this unit. All this at no extra cost. You can do it by just incorporating the processes in your organization. So coming back to the exercise what we started with earlier, the design for quality and reliability objectives, we have looked at the DFA, we have looked at the DFM, we have looked at the tolerance optimization and the tolerance selection based on process capability. We have looked at the cost aspect, the life aspect. You can do it using SolidWorks simulation, which is sitting inside SolidWorks. You can do the design studies there itself, and you can do the optimization of the individual characteristics of the component design parameters, keeping many aspects in picture. See, I'm reminded of one instance in the past where one of our customers was developing a tool holder. And he was doing it in 2 dimensions using a 2D software. And he had bought a very expensive balancing machine from Germany. And he was using it for dynamic balancing. We all know that static balancing you can do, dynamic balancing you can do up to second harmonics, and preventing the higher ones would cost you more money. So at least if we have the moving vector method and we start looking at the tolerances and building up the models based on tolerances, and we look at where to take the material out of the unit in an imbalanced system, using SolidWorks itself, using macros, using automation, you don't need to do a physical testing subsequently down the line. And for every time when the machine got repaired, they had to, believe me, send it to Germany to get it repaired and bring it back. All this was dispensed with by putting together the process inside. Writing a small macro, driving it every time you build the final model before releasing it, and it will tell you exactly where to put the counter mass, what should be the value of that mass, and then you do a sensitivity calculation based on your tolerances, and then you will be in a position to say what will be the level of vibrations that you will have on the bearings because of using this tool holder. This is an example which I thought I will share with you. This is more than two decades old. So what are these process-driven benefits when you incorporate this inside SolidWorks as a part of your design engineering practices? The first thing is your IPR. Second one is concurrent engineering. Your design review gets done by your concurrent engineering team. First time right becomes a byproduct of this, whether we see it or not. Enhanced reliability of the product, because all considerations have been put together in the checklist. The design confidence gets enhanced and the consistent quality is achieved downstream with nobody coming back and asking you for an engineering change, because every engineering change costs the company an arm and a leg in terms of money, because so many things get affected downstream. If we need to prevent all this, then these kinds of things can be incorporated as a part of the process inside your favorite tool, so that you can repeatedly go through these processes consistently, adhering to them. The input is provided, the process is there, and the output is there for everyone to see.